Hello, everyone. Thank you for coming. I know it's late in the day, and you're probably tired from having listened to a number of conference sessions before this, and I apologize for having to give you this presentation towards the end of the day. And I appreciate that you're here attending this talk. What I'm going to describe today is how we can do automated tuning of the JVM in particular, and for that matter, any device using Bayesian optimization. We've applied this to the JVM over the last couple of months at Twitter, and here I'm going to describe some of our experiences and what we learned. The presentation today is being done by Jianchao Liu, who's seated to my extreme right. Jianchao Liu was an intern at Twitter with JVM engineering when this work was done. Alex Wilchko, to my right, is with the Advanced Technology Group based out of Twitter in Boston. And I'm Ramki Ramakrishna, and I work with the JVM engineering group here in Twitter at San Francisco. The material that we are going to present here today was developed in concert with colleagues at Twitter Boston as well as Twitter San Francisco. And the technical work for the specific portion of the project that we are going to be describing today was done in concert with a bunch of engineers here at with JVM engineering as well as site reliability engineering here in Twitter San Francisco. So thanks to all of them for contributing to this work. A couple of words about who we are. Jianchao Liu is a graduate student in electrical and computer engineering pursuing his PhD at Purdue University. And I've already told you about myself and Alex. I want to start by setting up a bit of background for how this work came about. As many of you might know, Twitter is built out of microservices. There are a lot of microservices that make up Twitter. So when your tweet lands on Twitter property, you're talking with a service that's facing the web. That service will, in turn, hand off portions of the work that are required to service that tweet to other microservices. And these microservices communicate with each other and, in concert, accomplish the work that is needed in order to provide the overall service. Here I have a picture of all of the microservices that make up Twitter. At last count, there were over 1,000 microservices in the Twitter ecosystem. Each of these microservices might itself is typically built out of several instances. The number of instances might range for smaller microservices which have less load. They might be made out of maybe 10 to 15 instances. The larger microservices might be made out of hundreds or even thousands of instances. It turns out that the total number of service instances, which are basically, you can think of service instances as processes. There are over 100,000 service instances in the system at any time. These instances actually can range in size from single JVMs running with 1 gig heaps, or some that run up to 60 to 100 gigs of heap. So the sizes of the processes could be huge. I said JVM here, but many of our microservices might be built out of non-JVM processes as well. It just so happens that many of our microservices are written in either Java or Scala, and as a result, they're translated into Java bytecodes, which run on the JVM. These JVMs are scheduled, or these JVMs or processes are scheduled using Mesos into one of several data centers. These data centers might be made out of racks full of heterogeneous hardware. As you upgrade hardware, there's at any time a mix of different kinds of hardware in the system. And so any of these microservice instances might land on either an old hardware running a slow CPU or a newer piece of hardware running a faster CPU. In addition to that, each of these instances, or even the CPUs, even the servers on which they are running, might be built out of hardware that has maybe faster disks or slower disks, faster memory or slower memory, and a faster CPU or a slower CPU. So there's, suffice it to say that there's a large plurality of performance across the entire data center, and a microservice doesn't know where it's going to run. If we were to look at a performance stack at Twitter, so that gives you kind of the background of how we are approaching the problem. Supposing we were trying to tune a one of the microservices here, how might we do it? Let's look at one particular microservice here. On the left is microservice A, and on the right is microservice B, and these are two instances running in Mesos containers on top of a single slave, a single Mesos slave. So they share the hardware and run in separate Mesos containers. Now these containers themselves might run perhaps possibly other processes. The microservice runs on top of the JVM. Now if you look at the performance of this of one instance of this microservice, it could be influenced by hardware, the kernel, the Mesos container, characteristics of the Mesos container and how it's tuned, the JVM, the size of the JVM, the parameter settings of the JVM, and finally the parameter settings of the microservice. So the tuning problem here, in order to optimize the microservice, would consist of tuning one of, tuning many of these layers. So there are multiple parameters that feed into the performance that the service gives you. If you think of the scale of this problem, you have thousands of microservices running on heterogeneous hardware, and in a layered system, there's parameters that will dictate the performance of each layer of the stack, and the performance of the composite is determined by the performance of the settings of the parameters underneath it. Let's, for the moment, just focus on one particular layer of that performance stack. So let's take the JVM, for instance. I'm a JVM engineer. I kind of understand the JVM a little bit more than the other layers. If I look at the hotspot JVM, it has hundreds of tunable knobs. Here's a listing of the top few if I do a grep on the set of flags. It turns out that, in fact, there's a total of about 800 different flags. Now, not all of these are performance flags or influence performance, but there's a lot of them. There's probably over 250 or 300 different flags that will, in various ways, affect the performance of the system. So there's a large variety of parameters in the system. Some of them influence performance, others don't. For some of the parameters, the influence on performance is large. So small changes to that parameter might influence performance greatly. Some of them depend upon the hardware. So the optimal setting for that parameter might depend upon the underlying hardware. So the underlying hardware would influence how you'd set a parameter in the JVM. Some of the parameters are independent of each other, and others depend upon each other. So the setting of one knob might dictate how another knob gets set in order to extract optimal performance. Basically, if you think about trying to tune 250 parameters to get your system tuned optimally, it's a huge problem. It's an intractable problem. No human can attempt to do it, and even for machines, this would be impossible because of the large number of large combinatorics involved. We can attempt to solve this problem through hand tuning. But as the previous slide showed, even for one layer of the stack, there's a combinatorial explosion, and if you consider all of the other layers involved, then the combinatorial explosion, then it becomes basically a practically impossible problem to solve in practice. A few parameters might be handled manually. performance tuning is time-consuming, labor-intensive, and error-prone. If a human were to do these experiments, typically you would take a single parameter, run an experiment for a day or two, learn something from it, and then go on and review, change this parameter, and go on and try and see, analyze how the performance is changing, and then kind of go from there and try to see how performance changes. Now, because of the fact that it's a time-consuming and labor-intensive and error-prone process, it doesn't get done often in the data center. And especially at the scale of thousands of microservices, it's almost impossible for someone to keep up with this performance tuning load. As a result, what happens is that when microservices start up, for example, they end up cargo culting configurations. So if there's a certain microservice that's using a certain set of parameters, others will say, hey, maybe this works well because they've been using it. I'm going to use the same set of parameters. So this, and maybe they'll do a little bit of search around that cargo culted, parameter setting, but not a whole lot of attention is typically paid to this problem. Even if we were to spend a lot of time, now take the case of a large microservice. Let's say there's one particular microservice that controls the performance of Twitter. We might end up spending a lot of time trying to tune it. And we might achieve something close to optimality, but as soon as the JVM gets upgraded or the service gets upgraded, that optimal setting is no longer optimal. It's probably already become suboptimal. In other words, any setting that we find is optimal only very transiently and very soon becomes suboptimal. So our hypothesis is that most microservices operate below optimality because of the rate of upgrade of the service and its underlying stack. As a preview of the results that we're going to be showing, we picked one of the largest microservices that we operate, and through applying machine learning, we were able to extract about 80% improvement in its performance. Let me step back a little bit and talk about how performance tuning can be optimized as a formal. Can be cast as a formal optimization problem. So we have, you can consider a function f, which is our performance metric, which we are trying to optimize. And this is influenced by parameters x1 through xn, which are defined over some domain. What we have to find is a setting of those parameters that maximizes f. That is the performance metric that we are trying to optimize. That's the unconstrained optimization problem. In practice, there are constraints on the system. Just as I noted earlier, some parameter settings might influence others. So for example, if I were tuning the JVM, I shouldn't be able to set the new size larger than the heap size. It would always have to be less than the heap size. So that's a simple constraint on the parameters. Or I might say that the maximum tenoring threshold that I set for the garbage collector should lie between 0 and 15. There could be more complex constraints on the parameters, which influence how you can tune these parameters. All of these can be modeled in the optimization tool that we'll be talking about. There could also be, in addition to the constraints on the parameters themselves, there could be constraints on the behavior of the system. So for example, even if I'm optimizing some performance metric f, which is a function of the parameters that I'm tuning, I might have other further constraints on the behavior. So for example, I say that I want to maximize throughput, but I want to maximize it subject to latency staying below 5 milliseconds, for example. The 99th percentile of latency should stay below 5 milliseconds. Or I might say I'm willing to increase throughput just as long as there are no errors. So that might mean that the responses sent are equal to the request received. So those are the kinds of constraints we might want to model. But what makes things even more complicated is that the performance function f itself might be noisy and non-stationary. And why would this happen? This is something that performance engineers see all the time. In the picture that I put up before, there were two different microservices instances that were running in two different containers on the same host. Because of lack of because we don't have perfect isolation, there might be crosstalk between the containers so that whatever is running in your neighbor might influence your behavior. This would manifest in the form of a noisy performance metric. There might be seasonal or diurnal variations in the environment. The load might vary throughout the day, and what is optimal at one load level might not be optimal. A performance setting at one load level may not be an optimal setting another load level. And finally, in a virtualized data center, usually you don't have control over the hardware where you're going to be running. And depending on the hardware where you're running, the optimal setting of parameters might vary. So if you just look at the metric, the performance metric as a function of the variables of the parameters, you'll find that it's noisy because it's running on either one kind of hardware or a different kind of hardware, and the value of the performance metric varies. How might typical, this basically says what a typical performance tuning strategy might look like. We would find a suitable performance metric to optimize, and this is something that the service owner will typically come up with. He'll say, hey, I want to optimize these parameters, these performance metrics. And he might start an experiment, and then in the course of doing that, he might realize that the performance metric he's defined doesn't capture all of his requirements. And so there's a process of refining that performance metric until you find the right performance metric that captures all of the desired, all of the performance envelope that you're trying to capture. And then you might look at that, and then you might look at the underlying system and say, okay, what are the knobs that I have here to tune? And obviously, for example, looking at the JVM, you can't pick all of the knobs. You pick a small subset depending upon what you think is sensitive, the performance would be sensitive to. And then you use an iterative strategy, both collecting data and perhaps refining these knobs further. Here's how it looks, how it might look pictorially. And we've got the performance engineer sitting there measuring performance, looking at the data, analyzing it, and picking a new set of parameters to test based upon the results obtained. Note that each of these experiments can be a fairly expensive experiment. So I can't actually end up running thousands or millions of experiments and maybe mapping the entire optimization space and pick the optimal setting. I have limited amount of time, and in that amount of time, I should be able to reach an optimum. I don't have infinite resources. How might I make this faster? Maybe I have a black box tuning assistant. So instead of my running the experiment evaluation, the black box tuning assistant will suggest this is a set of parameters to try, and then the system being tuned will then run with that set, which we call an evaluation. And based upon the results obtained, the black box tuning assistant might analyze this, look at the history of the results obtained so far, and make a new suggestion. And this is precisely what my colleague Alex is going to describe in the next few slides.
Hi, I'm Alex. So I'm going to move this up a little bit. So we want to build a black box optimization assistant in order to speed up the process of tuning, particularly here at the JVM. So at Twitter, we've done this using a machine learning technique called Bayesian optimization, and I'm going to tell you how this works a little bit. It's a machine learning approach to black box optimization, and what it is a method to learn the cost function you're trying to optimize. And I'll show you this pictorially in a second. And it does so iteratively, and in practice, it works quite efficiently and finds very good answers to tuning problems very quickly, and we've found that it works very well on a wide variety of problems. So here's kind of a cartoon setup. So I'll show you this one-dimensional tuning example. It's on synthetic data, but I'm actually going to show you our actual model that we run in production, kind of digesting this experiment. So let's say in this imaginary tuning problem, there's an imaginary engineer that over the course of 6 months or so has tried 3 different parameter settings for a very large important microservice. And each of these dots might have taken days or a week to get, right? So these are very expensive experiments, and what this engineer is doing is she's tuning the parameter that affects performance in order to, some parameter that we've actually got control over in order to increase performance, right? So the x-axis is something we have control over. It might be a flag in the JVM. And the y-axis is performance, and we always want to be higher, right? So 3 here at the very top of this plot might be 3 million requests per second. It might be 3 million new users, $3 million in revenue. It doesn't matter. It's just something that we want to make higher, right? So that's kind of the setup. So how do we pick the next best experiment to try? It would be trivial in a world where we actually knew the cost function that these experiments were being drawn from. However, this dotted black line, which is the true function, is completely inaccessible to us. In order to learn that whole function exhaustively would take an enormous amount of effort. So we really can't hope to actually ever learn the true cost function. But what we want to do is find that third bump there, that maximum around 3. And so this is what we turn to Bayesian optimization for. Bayesian optimization is a technique that will build the best model that it can with the data that it has available, right? So the blue line there is our model's best guess of what the true objective function is. And you'll notice that it doesn't match the true objective function very well yet, right? We only have 3 points. And our goal will be to suggest new experiments to try in order to learn what's actually going on. And the faded blue there is kind of the part that puts the Bayesian in Bayesian optimization. That's a representation of the model's uncertainty at any given point along that parameter, right? So we have the ability to predict what we think performance will be at any given point, but we also have a measure of how confident or uncertain we are at that point as well. So that's what being Bayesian is all about. It's about quantifying your uncertainty, and this turns out to be pretty critical for the performance of models like this in low data regimes. So how do we actually pick the next point from this model? So we have a model, but we don't yet have a way of actually suggesting what to try next. And whenever we're going to try to make a new suggestion, we have to balance 2 competing desires. The first one is exploitation, and the second is exploration. So when we exploit, we try to pick a point that does as best as we can manage given the information we have now, right? So that might be a point near -2 or something like that. Versus exploration, where we try to learn as much as we can about the function in the hopes that eventually we do better, right? So that might be a point on the far left or somewhere between 0 and 4. So there's actually, oh, thanks. So like we would want to explore the kind of fuzzy regions, right? So there's actually a way to balance these 2 things pretty naturally, and it's an old idea from about the 70s, and it's called expected improvement. And I'll show you how we calculate that. So you calculate expected improvement in the following way. You take your best point, and you slice off your probabilistic model. So I've got probabilities all along here, and I just slice them, and then I sum them. And when I sum that, this is what I get down here in this red line is expected improvement, right? And it balances exploration and exploitation in the following way. I can kind of give you an intuition for why it makes sense. And that's that you are exploring, but only in areas where you hope to actually get an improvement, right? So by slicing off the probability of things that are better than your current best, you're only looking at things that you think might be better than what you've already seen, right? And I can actually show you how this process of suggesting works, where we'll just basically say, oh, you should try the point with the highest expected improvement. So if we try that previous point, we've got another one here. It's changed both our model and our expected improvement, and now we're actually doing Bayesian optimization now. We're suggesting experiments for a service engineer to try. And we'll try another one, and another one. And at this point, we've basically learned as much as we want to know about this plateau from -1 to -4. And you'll see that our model spotlights have kind of turned towards 2 separate regions on either side of this area where we know quite a bit. So we'll try another point there. We get a bit unlucky, and that's a point to take note of, is that when you're doing these kinds of tuning, you have to be tolerant of bad suggestions, just because there's no way of knowing what's going to happen ahead of time. So you need to be able to kind of quit your experiment quickly so that it's not catastrophic. And with some knowledge here, we've basically scooted what we care about over to the right or to the left. We try 1 point on the left, and that's enough to kind of shift our focus back here. And we very quickly hone in on the global optimum, right? So that is what Bayesian optimization actually looks like. This was a real model, the kind of one that we run in production, but running on some kind of fake data. I did a one-dimensional example just so that I can put it on the screen, but Bayesian optimization works in 2 dimensions or 3 dimensions. We routinely tune problems that are 2 or 3 or 4 dozen parameters that have that many parameters. And it still works efficiently. As Ramki mentioned, if you've got like 1,000 parameters, there's actually no method that you'll find that does that efficiently. It's just statistically a very difficult thing to kind of search in. So there are practical limitations, but the advantage of using an automated tuner, even one that doesn't kind of work in 1,000 dimensions, is that once you get past 3 or 4 parameters, your visual system doesn't give you really good intuitions of what's actually going on anymore, right? You can maybe do 4 dimensions if you add color to a 3-dimensional plot or something like that. But after that, we basically don't know what's going on. And it might take actually 10 years to gain enough intuition to work in 6 or 7 dimensions. Maybe people can do that. But as the dimensionality grows, the comparative advantage of Bayesian optimization over humans also grows, right? Up to a point where it's statistically kind of intractable. So that's kind of the advantage of using an automated approach like this. But what do we want it to look like in practice? So this is kind of a service for a service. It's like a meta service. And we kept that in mind when building that. And we wanted to make this extremely easy to use so that we introduce the minimal mental overhead to the engineers that are already worrying about reliability and correctness. And then when they come to tune something, we really don't want them to add a whole other technology to their brain space. It really slows you down. Or they just simply won't use it if it's too difficult. So it had to be easy to use. That means minimal coding. That means multiple languages, whatever people are writing in or feel most comfortable in, they have to be able to interact with this service in that language. And also, because of the time constraints of extremely expensive experiments, you want to be able to run multiple concurrently, right? So if your experiment takes 10 days, and you can run 10 in parallel, you've just saved an enormous amount of time, and so concurrency should basically be free. So this is what the API looks like. This is our Python API. So you import WetLab. This is just our internal name for the Bayesian optimization service. And then you define an experiment set with a name so you can find it later. And then you tell the Bayesian optimization service the specification of your problem. And so here for value A, I've got a float from 0 to 1. We default to float. B is similar. And value C goes from 0 to 10, but it's an int, so we only suggest like 0, 1, 2 on to 10. And then value D is an enum type. So we've got red, blue, and green. And the difference internally is for our Bayesian optimization service, integers, we actually learn about the ordering, like how the function will change in an ordered way, whereas enums, we throw away the ordering so that we don't kind of confuse red, blue, green for 0, 1, 2. And then this is basically the entirety of the API for interacting with the service. You say, please suggest me a suggestion. Right? When you get back as a dictionary where the keys are value A, B, C, and D. And the values are numbers in between these bounds or inclusive of those options. And then this test my service function here is something that the service engineers have already written. It's a performance testing suite that I'm just going to assume exists. And it can take a configuration and then run their whole performance testing suite. And then they've defined and thought carefully about the single number that they think constitutes performance of their service. And here I'm just calling it service throughput. And then once this is run, and this single line might take hours, days, weeks, cost thousands or tens of thousands of dollars to run, right? This might be extremely expensive. And then you say, hey, Bayesian optimization service, with this suggestion you gave me, I did this well. And then this whole thing can be in a for loop if you want to run 10 of these on one node, or you can run this concurrently. You can have 10 copies of this running concurrently on the same node or on separate nodes. And this concurrency is supported by the kind of design of the service as we have it. So all of our clients talk to a web server that through some middleware populates a queue of suggestions that you ask for. The queue is drained by an auto-scaling group of workers that actually implement the machine learning numeric code that we have. Right? So asynchronicity from the perspective of the clients is basically free. So Bayesian optimization there is actually pretty expensive to run in terms of compute time compared to other alternative approaches. So you're not going to hit this endpoint and get 1,000 suggestions per second. You might have to wait a couple seconds, or in the case of like 50 dimensions and then 500 previous results, you might actually wait a couple minutes. Right? So Bayesian optimization really shines in the condition where your experiments are so expensive that you don't mind waiting a minute for a really, really good suggestion. So that's kind of the regime that we're in. And Bayesian optimization isn't really the only technology that you can use to make suggestions like this. It turns out that if you just systematize the process of tuning, as in this kind of a system, random search is actually not that bad, which is really surprising. People actually write papers about this, kind of in the field of machine learning. But if you are going to do anything, investing in systematizing the tuning process will get you, almost half the way there. But doing random search for the actual suggestion engine is a pretty good place to start, especially for high-dimensional problems. In fact, you can prove that, or you can, I guess, show or intuit strongly that for like thousands of dimensions, kind of in the limit, you're basically just as good as random search, right? But in this regime of like 5 to 50 dimensions, you maybe want some smarts, and there's some other alternative approaches. Here's a couple listed: reinforcement learning, random forest, parsing trees. These are kind of technologies to be aware of. We prefer BayesOpt because it's robust. We have a really robust code base that does this. It's extensible, and what I mean is the mathematics behind Bayesian optimization allow for the addition of new features. So Ramki mentioned optimizing with constraints. This was something that was actually pretty natural to add on the mathematical side to the system. And in fact, our Bayesian optimization system has been refined slowly, starting just from a purely continuous case, adding features as we found them. It's just been very natural to do this using the kind of setup that I've mentioned here. But most importantly, it's really battle tested at Twitter. We've used this on a lot of real world high impact problems. We've helped tune the spam and abuse detection models. We're not the only people trying to make this better, but we've kind of done a similar flavor of what I've talked to now. All deep learning at Twitter, and this is kind of a growing segment of technologies that we're investing in, go through Bayesian optimization tuning before they go into production. It's kind of just a part of the workflow at this point. We've seen a really big boost in user engagement. There's a particular recommendation feature on Vine that's seen a really big boost of user engagement through just tuning the knobs on the algorithm, right? They didn't write a new algorithm, they just tuned it. We've seen a pretty dramatic cost reduction in an extremely large Hadoop batch processing job. We could probably have a whole talk on this. This is being used in the revenue org. And then what we're here to talk to you about today is tuning JVM performance. So I'll turn it over to Jen Chow.
So thanks, Alex. So based on the introduction from Ramki and Alex, we are going to tune a group of JVM parameters to achieve the best performance. So here's a parameter list we are using in our system. There are around 5 to 10 common tuned parameters, plus a bunch of others based on gut instinct to make the number of parameters to around 30. So to tune even more parameters, one have to periodically walk through the parameter set, and at each level or each module that is being tuned, rank them by their importance, and use some strategy to iteratively walk through the block of parameter. So this is because the BS service we are using cannot effectively handle more than 30 dimensions at a time. So as mentioned in previous slides, although there may be a lot of parameters that will take effect on the service performance, a typical strategy is to divide the problem and optimize for different layers. So here, these are layers that may of interest to a particular tuning exercise. So you may see the lower layer is shared by the upper layers. That means if we want to tune the kernel parameter, we have to take all the microservices into consideration. In the project we did during the summer, we only constrain ourselves on the JVM parameter. But in the future, we want to add more parameters from the service, the kernel, and even hardware. So we decided to kick the tail of our approach from a very simple JVM benchmark named as the Spec JBB 2015. So it provided us with several very important insights, including the effect of platform heterogeneity to the system performance, the value of optimal, and the stepping up issue when the Spec JBB do the stress test for the peak performance. So with those experiments under our belt, we decided to switch back to our original problem, named as tuning the JVM parameter to optimize the performance of our real production microservice. So the microservice which we picked manages the access to the real Twitter user-related data. So it is a core service to the tweet, write and read, and the population of timeline. So the reason we choose this service is that it doesn't undergo frequent redeploys, and it has a large number of service instances. So here's a logo for the mysterious microservice. And about the evaluation environment, since our eventual goal is to apply the tuning approach to a production version of a microservice, we decided to gain experience in a so-called staging environment. The staging environment will receive real production requests, although these requests are read-only. And we set the performance metric as RPS over the GC cost, which is requests per second over the time spent on GC. So this is the result of the discussion with the microservice owner. He spent extensive effort on choosing this metric. So he's more professional than us. We just use it. And the response latency is indirectly present by the GC cost. So here's the structure of our tuning system. Just take a look at the microservice block. We have 5 shards in total. For every time, we only do experiment with shard 0. And we set the shard 1, 2, 3, 4 as a baseline. So due to the limitation of Aurora scheduler, at least the version we are using in Twitter, we cannot specify a certain platform to launch the shard 0. So we have to restart it multiple times to get a matching platform. Usually, we start from getting suggestions from the BSOpt service, and our JVM tuning service will generate a real JVM configuration and upload to the file store service. So after this, we will check what kind of baseline do we have. So here we have four baseline running on 3 different platforms. So different color means different platform. And then we keep stop and restart the shard 0 to get a matching platform. So here we find the shard 0 is running on the same platform as shard 1 and shard 4. We will let them run for a fixed duration and then recheck the baseline. So we may find that during the test, the shard 1 is restarted by the Aurora scheduler, so it's invalid. Eventually, we only get one valid baseline, which is shard number 4. And after that, we'll try to get the performance score from our observability service, get their score, and compute the ratio, and return back to the BSOpt service to start a new iteration. So here's a real performance score ratio over the iterations. The higher, the better. You may find our BSOpt always try to give good suggestions. Meanwhile, it also try to explore the space to learn more information. So the black line here means the shard 0 performs the same as a baseline. So any points below this black line is a bad suggestions. Our service can tolerate very bad suggestions. So overall, you can find we are getting better and better results. So how good are they? Let me show you in the following slides. So here we just pick the best result in this figure. So in this figure, the blue line presents shard 0 running with the tuned parameter, and the yellow line is tuned by Twitter engineer. So you may find the blue line always perform better than the baseline. According to our performance metric, the shard 0 performs 80% better than the baseline. If you can remember, the performance metric is RPS over the GC cost. Is there any improvement from the RPS? Let's take a look. So here you get it. During the test period, the RPS, they are almost the same for the shard 0 and the baseline. So that means all the performance benefit comes from the lower GC cost. Actually, our tuning system can reduce the GC cost by 45%. So how do we get this? Because of the Bayes optimization service, of course, and because of the Twitter infrastructure and the smart engineer, of course, and even more. So we spend we spend a lot of effort on the real, engineering details. So the first one, we make sure every time we do the apples to apples comparison. So there are more than 50 different platforms in Twitter. So every time we restart the shard zero to find a match platform. So this is very important to get a good tune result. And second one is the system service could cause failure. Sometimes they could time out, they could return empty content, and even cause some exceptions. We have to handle all these details. And the most terrible one is sometimes the Aurora scheduler will try to interrupt the instance. For example, the shard 0 and shard 1, shard 2, shard 3. If we find the experiment is interrupted by Aurora, we have to rerun it again. And the last one is the authentication service could time out. So this is designed by authentication team. We can't change this, but we have to deal with it. Here are some steps we hope we can do in the future. The first one is we want to do some concurrent evaluations, and we want to choose a longer experimental duration. So a longer duration will make the system more robust to the noise and the changes in the system input, but it will also make the experiment much more expensive. So that's just why we choose a Bayes opt, because it can get the optimal with much fewer iterations. And we also want to design different experiment set for every hardware platform and terminate some very suggestions before it goes to the end. And we also want to do the stress test to validate some optimal configurations and extend the framework to an arbitrary microservice. So at last, we also need to clean up the authentication problem and replace some better APIs.
Thank you, Jinshao. Thanks for that nice description of the work he carried out over his internship this past summer. And I'm going to share with you some lessons that we learned. So focusing on the optimal result that he was displaying in the previous few slides, if you recall, he'd put up a set of maybe 7 parameters, and then there are dozens more. We'd actually experimented with something like 40 different JVM options. How did the optimal compare against the baseline, and what did we learn from it? Obviously, any lessons from here don't translate. You can't take specificity of the settings that we have here and expect that it'll work in any arbitrary microservice. This is specific. There are things about this microservice which might not translate well to another one, and in fact, there would be some that might translate, others mightn't. So you have to, take these results with that caveat in mind. So one of the things we found was that, for example, the new generation size. Now, at Twitter, as you may have seen from previous talks from my colleague Tony Printezis at earlier Java 1s, etc. At Twitter, we run with very large Edens and relatively small old generation sizes. Because there's little state in the microservice instance. It turns out that Bayesian optimization actually found that, and it came up with similar new generation sizes. No surprises there. The surprise was only that a machine was actually able to figure that out. It found that the tenoring thresholds and the survivor space sizing that was done manually may not have been the most optimal. And there's a lesson here. This service was probably optimized a year and a half, 2 years ago, and no one came back to look at it. Bayesian optimization, within a couple of days, was able to find that was a suboptimal setting and shift it to a more optimal setting. And therein lies the power of this, that we can actually, this is amenable to automation, which will continuously optimize your system and be able to, even though the system changes, the layers of software get upgraded, the hardware gets upgraded, it'll still be able to readjust the service settings so that it's always operating optimally. It found, for the third bullet over there, it found that the prefetch read interval that GC scanning uses in order to prefetch cache lines ahead because it's going to be scanning those, it found that that was too small. Now, this might be very specific to the sizes of objects that we are using here and what GC happens to be scanning. But it found that for this particular service and on this particular hardware, that size was, the prefetch interval size was too small, and it said we should use a larger setting. And this sped up GCs as well. There's a very infrequently talked about allocation filter in the old generation. So when we're promoting objects into the old generation allocator is asked to allocate an object of an arbitrary size. And there's a certain filter that looks at the incoming request, the allocation size stream, and it decides that it needs to pre-populate caches so that they have the right amount of data of the right sizes, objects of the right sizes. And there are certain filter parameters that are looking at this and smoothing it out in time and figuring out what the sizes of those caches should be. And it turns out that the default setting of those filter parameters were suboptimal. And this is something that no one tunes. I mean, I'm a GC engineer. I actually put in those filter parameters. I never tune them. And it turns out that, in fact, there are settings which are, which can be found automatically, which work much better. Somewhat surprising to us was that the number of GC threads that we should run with for this service is larger than what we might think of setting. And this is, I think, specific to the environment in which we are running, in which we have somewhat underused cores so that we can actually run more GC threads than are available, than the number of cores that are available to the container. And finally, we found that there's a compilation size threshold that is used by the JIT to do inlining. So if the amount of inlining that we do results in a very large method, then at some point the inliner will stop and say, okay, I don't want to inline more because the resulting method might become too large. It turns out that in this case that threshold setting was perhaps too low, and by having a larger method compilation size threshold, it turns out that you can inline more, and as a result of that, you can escape analysis will find more opportunities for stack allocation. And as a result of that, your allocation rate will in fact come down. So your GC, the frequency with which you need to GC would come down. And that's another thing that contributed to better GC numbers. Overall, what can we say about the performance gains? We reduced the GC overhead. Well, but the GC overhead was not very large to start with. Maybe it was 1 to 2%. That's not a great gain. But what it resulted in was that the tail response latency shrunk drastically. It became half of what it was before. So looking at the 99th percentile, for example, 99.99th percentile, it became much lower than the service level guarantees that the service was providing. In other words, now we can drive much higher load through that single service instance without hitting the thresholds, the pain threshold. What that means is that you can now run fewer instances to take the same amount of load. And that translates into bottom line savings. Operational costs are lower. You need to have fewer servers serving the same amount of load. What if you could do something like this continuously on all of the services that exist at Twitter? We think there's great promise in this, that we could extract a lot of savings through applying this program systematically and continuously through our infrastructure. There were a lot of lessons that we learned. I'm going to skip through this in the interests of time. The choice of performance function is something which you have to kind of do and gain experience from, but we believe that most of the service owners out there have already put much thought into it. And so it is usually a small matter for you to use existing SLAs as the performance metric that you're going to optimize. The choice of parameters to tune, you would have to go and look and talk with perhaps experts at each of the layers in order to figure out which parameters to tune. But these are one-time costs that you pay. Once you've got that going, that program going, the continuous optimization can then be done in the background by your machine. You have to, as Jinchao mentioned, we have to protect against noise in the data center. There are lots of, as we noted, there are lots of ways in which results can be noisy. And for Bayesian optimization to work well, the less noise, Bayesian optimization, to be honest, actually is able to deal with noise. But the less noisy we make the performance metric, the faster it'll converge with fewer iterations to an optimum. And so we found that, for example, it was worthwhile taking longer duration experiments, in other words, more costly experiments, to make the performance metric less noisy and thus be able to actually converge much faster to an optimum result. I'll skip over things like long-range effects. If there are questions, we can deal with them at that point. And finally, the point I want to stress is that the amount of, this work was actually done by Jin Zhao in a couple of months. That's because the microservices architecture already provides most of the hooks into which we can hook in. There's lots of existing monitors and alerts so that we can terminate, for example, suboptimal suggestions that might be made by Bayesian optimization. There's enough resiliency and redundancy built into the microservices framework so that 1 or 2 or 3 instances might be running suboptimally without affecting the performance of the ensemble as a whole. And without affecting SLAs. There's extensive telemetry into which you can tap into so that you can have complicated performance metrics and performance functions. You can, as you refine your performance metric, you can tap into lots of existing telemetry and make your optimization process much more effective and much more efficient. And of course, so basically, I want to end this talk by saying that continuous, inexpensive, automated optimization of the microservices is possible. And in fact, we believe it's inevitable because no human or team of humans can deal with the scale of this problem. It's huge. And Bayesian optimization, because it can find an optimum through experiments that can be potentially costly, but very few such experiments be able to find an optimum, holds great promise in being the tool to leverage when doing this. And finally, for those of you who've been looking at this and thinking maybe this is going to happen, what I want to stress is that the upfront costs of getting something like this working in the data center is actually quite low because much of the infrastructure already exists. We just have to tap into that infrastructure. And there are some lessons to keep in mind in terms of noise, et cetera, which will make this work efficiently and continuously. And that's what we hope to do in the future. Thank you for listening. Sure, questions?
Is the mic's on, right? This is on?
I'll repeat the question.
We'll just repeat the question once you ask it.
Right. Yeah, so actually, as I mentioned right at the outset.
Repeat the question first.
Oh, yes, right. So the question was, has the JDK team at Twitter, Twitter has a dedicated team of JDK engineers, has it looked at these results? Now, it turns out that, in fact, I'm with the JVM engineering team. So the JDK team is the JVM engineering team. And this was an effort by that team. And one of the reasons we actually did this is because we found that the scale of the problem is immense. And a small team of engineers can tune the JVM perhaps for 1 or 2 or 3 microservices. But with 1,000 microservices, you cannot hope to get an optimum that works across them. You can perhaps do so for a small number of parameters, but to make find something that's optimal across the range is impossible. And have we looked at the result? Yeah, in fact, we were actually, one of the things that we found, when people come to us and say, tune this microservice for us, we tune it for them, and they go and make use of those parameters. We pick maybe 5 or 10 or 12 parameters that we are familiar with and which we know the performance is typically sensitive to. We never go and look at the 200 other parameters that are there, which have been forgotten and lying dusty in the attic. And with Bayesian optimization, we could actually, when we were talking with Alex, we said, how many parameters can you deal with? And he says, oh, about 30 or 40. So we found about 10. Then we said, we can provide another 20 parameters. So we went and just picked some, not at random, but with some thought. And it turned out that we were very surprised, as I was trying to show in my talk. We were very surprised about how Bayesian optimization actually was able to find optimal settings for these parameters. And so, yeah, we are very happy with this, with the results. Let's have here.
I can answer the machine learning side of it.
Sure.
So, how can we try this out? I mentioned in the talk that just writing a system or building a system that keeps track of and systematizes tuning is really a huge first step. And then adding random search to make your suggestions is a perfectly fine place to start, especially if the dimensionality of your problem is large and if you can tolerate failures. So once you've done that and you're unhappy with random search because it's random, then there's a lot of options out there. The service that we have internally is like, I guess, 3 or 4 generations past something that's open source called Spearmint. I don't understand fully the licensing implications and if you can just plug that into your system, but it does exist. And then I think there's another piece of software called, or there's a company, there's a couple companies out there that will do this for you if you just search for like hyperparameter tuning. But Spearmint's open source, and I think there's links on that GitHub page.
Thank you.
But did you do this, the tuning with live servers, or was it replay data that you did?
It was live. So as Jian Chao indicated in his talk, in his section of the talk, it was in a staging environment, which means that this is not running production. It's not the production servers, if you will. It's another set of servers, but they receive traffic from production loads. Basically, yes. And the only thing was that because the incoming traffic might actually update state in the service, which would happen with write requests, for example, to the service. The write requests were not tapped. Only the read requests came in. So that's what we call dark read. So this was dark read traffic in a staging environment. But as we indicated, this was because we were trying to learn about how this works. We are now gathering enough confidence that we should be able, in fact, given all of the characteristics of fault tolerance and so forth, and resiliency that I talked about, we think the right way to do it is, in fact, to run it on production instances. For example, the write traffic might actually change the optimum. Something that was found to be optimal for only read traffic may not be optimal for write traffic. And so the eventual goal is, in fact, to run it in production. So you have this background thing kind of churning away and finding optima. It's going to get some suboptimal suggestions, but eventually we'll find the optimum. And so you want your service to be resilient to such suboptimal performance occasionally. Yes. Right. So the first question, I'll actually mention the questions and answer them one after the other. So the first question was the collector, the garbage collector type, right? Was the garbage collector type fixed for this experiment? Yes. So it turns out that, in fact, we use the same garbage, even though we mentioned that as one of the parameters that one could tune. We picked the garbage collector that the service was already using. This was the concurrent mark and sweep garbage collector. Now, in theory, you can actually make that another, because Bayesian optimization allows you, any set, enumerated parameters. You could have enumerated types. You could have the garbage collector as a parameter to the experiment. We haven't tried to see whether or not, so there are various ways of doing this. The thing is that if you change if you make the garbage collector one of the parameters, it'll take you probably longer to get an optimum setting. But yeah, it might turn out that maybe the G1, there are certain settings with G1 which might work better than with CMS.
So I read this part of code, so I can understand. I can answer this question. Actually, our code already supported to switch between different GC garbage collectors. We already supported this feature, but we just haven't tried.
Yes.
Yeah.
And one of the things is that there are lots of parameters, and depending on how you pick them, you can throw a lot of them into the mix. But it really depends. If you throw too many, then your convergence to an optimum would be slowed down because you'd need many more points, right? I mean, think of the optimization surface that one garbage collector presents versus another garbage collector. It's two different. They could be radically different. And to learn that, Bayesian optimization might take a little longer. So if the performance engineer has some idea as to where the optimum might lie, it might make sense to fix that. But sometimes performance engineering gut instinct may not be that good, in which case maybe you want occasionally to allow much more latitude in the choice of parameters and let Bayesian optimization find you the optimum. The second question was about whether or not we've used this for throughput-oriented processes. Now, it turns out that in fact, the microservice we were showing you is both throughput and latency sensitive, right? I mean, in some sense, by pulling in the latency, we managed to be able to push more throughput through more load through a service. So I think the two are kind of related. And yes, you can apply it to either, and it depends upon how you encode your performance metric. Yes, and that's what the performance engineer would have to do. He'd have to choose a specific performance metric, and the shape of that will determine. And you can have a combination of performance metric, a composite performance metric, possibly. And I've forgotten the third question that you. Yeah, so so we weren't paying attention to whether or not as this experiment was running, the service was being upgraded, the GRE was being upgraded. All of this our experiment was oblivious to it, and so at some point, so you have a system that's kind of shifting underneath, and it's eventually finding you an optimum, and that might be suboptimal because of changes in the layers underneath. One of the reasons for picking a staging environment is because we were doing research and we wanted things to kind of stay constant. And for the particular data that was presented, we didn't upgrade the GRE. It was done with one. It is possible that with another GRE, the optimal settings might change. Okay, let's have one in the back over there. Yes. Right. So that's a real concern. So the question is, how do you deal with peak loads that might never manifest in the measurement intervals ever during your testing, or you might be doing a measurement at a point where there was high stress peak loads, and those might make your performance metrics poor, right? And so you might end up actually going in with periods with settings that you measure in periods when loads are low, for example. How do you know that that's an optimum? And yes, and that's what Jianchao was showing in his slide, where after having gotten a bunch of optima, you could have a stage where you stress test them to find that whether or not all of them will withstand the stress loads that you expect the system to withstand. And so that would be a longer experiment. It might even be a synthetic experiment where you subject synthetic load on your system. So yeah, all of that will have to be part of the DevOps workflow should this be brought to bear in production environments. Question?
Considering the results of your experiments, do you think it makes sense to revise certain JVM defaults, like completion thresholds and so on, or tune ergonomics? So
Yes.
do you have plans to contribute some results of your experiments back to OpenGDK?
Yeah, so the question is, as a result of the lessons learned from this experiment, are there changes to default settings that we can contribute back to the OpenJDK? That's a good question. However, we have to remember that this is one data point, one microservice on which we collected this data. What we hope to do is run this across all of our microservices, and maybe in the greatest common factor, if you will, of all of these settings that we get, maybe there's some set of settings that's common across all of them. And that would be something that we would want to give back. What I wanted to stress here is that each of these microservices might have a different set of optimal parameters. And this deals with that plurality. But yes, if we find that there's some theme that's recurring over and over again, that's something that we might want to contribute back to OpenJDK. And that's something that Oracle might want to do as well. Oracle has its cloud thing. It might run this over across a lot of instances and find that it turns out that certain defaults are outdated and they need to be updated. This is something that used to be done manually many years ago. And now something like this can be done automated. So yes, that's a good way of looking at this as well. Let's have you. Well, the dream actually, so the question is, can this kind of performance optimization be part of the regular deployment pipeline? That's a good question. We have only this was a research project, and we have initial data that gives us much more confidence that in fact it can be done in practice. Now, before we started this, I'm a JVM engineer. I didn't know anything about machine learning. And looking at the scale of the problem, I would have thought that machine learning would never be able to give us results that are good enough to put into production. I was very surprised about how good and how quickly it found the optima. And if we put enough filters in the deployment pipeline to catch, basically the thing is it's important to design the experiment sufficiently well that you will not be caught in, you want to make sure that the optima that you find are sufficiently robust. They don't lie in, if you look at your performance surface, there are no tiny spikes in the performance surface that you've hit. And if you've done that, then what happens is some such small change in the environment can actually topple you from that performance peak to an abyss. And you want to avoid that. And so, I think more research needs to be done to see, how to get more confidence in the kinds of parameter settings that you have. And stress testing is a good way of actually finding that. So I expect that there'll be, in a deployment pipeline, there'll be Bayesian optimization coming up with a set of optima, and then something else filtering out the bad ones and picking the right ones based upon further tests, just like in QA. And then, and at the end of all of that, you actually have a set of golden parameters that you can put into production. At least that's our hope. Yes. The question is, how frequently did the optimal value change, and how frequently did you put it in production? This was a research project. We don't have it running in production. So yeah, these are things that we hope to learn as we progress further into the project. Okay, I think, let's see, what time is it? 6:36. Okay, I think that'll be the last question. Go ahead, please. Okay. There are two questions, and I'll take the second question first. So the second question was, you mentioned that there were a lot of parameters and you limited yourself to a smaller number. Yes, we did. And that's because Bayesian optimization, remember that the size of the problem grows exponentially with the number of parameters. Bayesian optimization does very well in controlling that combinatorial explosion. I'll let Alex actually describe to you the limitations because of which you have to limit yourselves to about 30 to 40 parameters at a time. Because the optimization engine, in order to make its suggestion, has to do calculations which tend to slow down.
Yeah, it's kind of, I guess the strongest answer to that question of the limit of the number of parameters is an empirical one, is we've just found that above 50 things take a long time. So it still works. It just takes, each suggestion takes progressively longer, and actually converging, so the number of iterations you have to run this takes a lot longer. And you can do really well if you just cut out if you do a little bit of thinking and you cut out stuff you don't think is related, or you try to combine things in interesting ways. But it's always an empirical question. So you could have 30 parameters and 29 of them could be junk, and there could be one that matters, and things will converge actually very, very quickly. And if you have 50 and there's one that's good, same thing, right? So this is just what we've seen in practice, basically.
And then the second question, the first question that is, which I'm answering second, was about the number of parallel GC threads. So so I don't know how many people over here know about Mesos containers. Maybe you've used them. I believe the increased number of GC threads that Bayesian optimization suggested is based upon basically the operating environment in this case. So Mesos containers take a certain, you basically can suggest that you require a certain number of CPUs, okay? So what Mesos does is it schedules you for time quanta of 100 milliseconds each on those many CPUs. So if it'll look at how much time your processors take, how much CPU time your processor has taken in that 100 millisecond interval. If it takes more than 100 times the number of CPUs you requested, then your process will get throttled. Now, if your GCs are extremely fast and your service doesn't impose a lot of load on the system, then, for example, let's say that your GC takes 10 milliseconds. I can actually run, and let's say that the system is, that your service is not doing any work or doing very little work in the rest of the time. So I can, for those 10 milliseconds, I can run 100 threads, right? And still appear as though I've stayed within the quota, because it is less than 100 times n for n CPUs. In this case, it turned out that we could run twice as many GC threads as there were CPUs available. And that's because each GC was blindingly fast, was less than 5 milliseconds. And so you never got throttled as a result of that. So I think it's specific to the environment. And it is possible that if there were higher load in the system, then this result would not hold. And so these are the kinds of things that you have to kind of look at when you get the optimal settings from Bayesian optimization.
That's kind of a feature of BayesOpt, is that it will exploit absolutely everything that it has available to it. And that includes if your performance metric doesn't, like there was a question, if your performance metric doesn't include something that matters to you, BayesOpt will effectively cheat, right? So it'll find a way to make that number as high as possible by surprising and frustrating you. So you really have to be very careful about how you define performance, and then you might have to be very careful about learning about why exactly your settings are good. Just because it only wants to make your performance higher, it doesn't care about anything else.
Okay, so thank you very much. And we are around here for another couple of minutes in case you couldn't get time to ask your questions. So feel free to come up and talk.